presentation is mine, and the title is the influence of metallurgical factors of corrosion fatigue strengths of stainless steels. And this is just a briefly outline of a corrosion fatigue design. As you know well, the steel, the airs, we have a very clear fatigue limit, but corrosive environment, we don't have nothing fatigue limit. So in case of the corrosion fatigue design, we have to think about the corrosion fatigue related factors. So if I say the difficulties in corrosion fatigue design is the no fatigue limit and time dependent, and also the corrosion fatigue strength is unknown. And of course we have three variables. One is material, and second is stress, and the third is environment. And today I'd like to focus on the material. So the metallurgical factors, the chemical compositions and heat treatment and microstructure for the stainless steels. This is a very old Japanese nature by Hirakawa and Tablel. And they did the bending corrosion fatigue test for 304 and 316. In the 304 cases, very long time, the suddenly reduction of corrosion fatigue strength. However, the 316 stainless steels, after the 231 days, no reduction of fatigue strength. This is because of the molybdenum content of the 316 stainless steels. So we tried to check the certain properties by use of ultrasonic fatigue testing, because we can get the certain giga-cycle data, and we chose the 304 and high nitrogen 304 and 316, and also the 250. This is the corrosion resistant seawater stainless steel, the 2.5 contents of molybdenum, and used 270 in the so-called super stainless steels. And their mechanical properties is the very high in the ranges of the almost 600 to 900 megapascals. And we did the ultrasonic fatigue testing by use of conventional Shimazu USF 2000, and frequency was 20 kilohertz, and error value was -1. And just simply we chose the air and the 3% sodium chloride aqueous solutions. But you understand the difficulty of ultrasonic fatigue test for austenitic stainless steels, because low conductivity. So we have to very careful to prevent the heating of specimen during corrosion fatigue test. And we did the circulation solution and compressed air, and also we tried the intermittent operation, so 110 millisecond up duty and 1100 millisecond repose. And this is one of the data for the 304 and 316s. It's the giga-cycles, and the reduction of corrosion fatigue strength of 316 is just a little higher than that of the 304s. And this is the super stainless cases. Very early number of cycles, just a little influence of 3% sodium chloride aqueous solution, but 10 to the 9 giga-cycles, no reduction of corrosion fatigue strength. So because this stainless steels have more than the 6.5 molybdenum content. And this is another chemical compositions cases, and 304 and 304 high nitrogen cases. And high nitrogen cases also the no reduction of fatigue strength at 10 to 9 cycles, because this is the high nitrogens environment. So this is the summary of this austenitic fatigue test, and you can see the reduction of the corrosion fatigue strength. And the next concern is the heat treatment. I chose the 13% chromite stainless steel. This is in United States and in Europe, and except Germany, they say the 12 chromite stainless steel, and it contains the 0.5 molybdenum. The very important things is the heat treatment and quenching, then after tempering. And in this case, the tempering temperatures is 700 centigrade, 700 C at 3 hours, and then after that air cooled. This is the best heat treatment. And this is the SN diagrams, number of cycles versus rotating bending stress. You can see the such a heat treatment, the quenching temperature 750 degrees centigrade is the smallest reduction of corrosion fatigue stress. But the this is the smallest, but the very high cycles in the 75% reductions. And the same material, we also tried the crack propagation test. And this is the dA by dN versus delta K. But in this case, you can recognize no influence of the 3% sodium chloride environmental corrosion fatigue crack propagation. So we can conclude the for these materials, the very important things is the crack initiation process, and the crack initiation process, and also a very important things in the initiation of the very small corrosion pit and growth of a corrosion pit. And most of the life of these materials, corrosion fatigue life, in the corrosion pit initiation and corrosion pit growth. So finally, I would like to talk about the certain microstructures effect. This is data for the suction roll material. These materials and suction roll cases, we had too many corrosion fatigue failures many years ago. And formerly, we were using the 13 chromite cast steel, but then after that, we changed to use the duplex stainless steel. This is very simple data, and fatigue strength versus 40% ferrite. Then we try the air melted steel and the vacuum melted steels. And the environment in the potassium arc at the 40 degrees centigrade. And these data are the 10 to the 8 cycles. And you can see the both metals, the around the higher the boron percent ferrite, the higher the fatigue strength. And also the same manners, we can see the corrosion fatigue strength. So I think most of the cases, the data shows the around 60 to 50 to 65, the maximum fatigue and corrosion fatigue strengths we could get. So if I say concluding remarks, and metallurgical factors contribute to corrosion fatigue strength improvement, molybdenum content for austenitic stainless steel, and also the tempering temperature for 13% chromium stainless steel, and 40% ferrite for duplex stainless steel. And these metallurgical factors are strongly related to corrosion fatigue formation, that corrosion fatigue crack initiation process. But however, the corrosion fatigue initiation mechanism and the evaluation of the corrosion fatigue crack initiation is nothing vivid. So we have to do the further investigation. Thank you very much for